A very good morning to all the students, to all the friends, to all people who are watching these videos, uh, uh, and especially I'm talking about the students. So in this video, I'll be talking about. I'll give the brief introduction of nanotechnology. What I intend right now is that I believe that I'll be preparing a course on nanotechnology, and basically uh, uh, I will include those topics which are from condensed matter physics. I will include them in this series, and I'll try to connect it to the physics of nanomaterials, to the physics that leads us to understand nanotechnology. So here, what my intention is that before I prepare and draft those videos for you, I would like to introduce you with the subject and the framework of the subject and the credibility of the subject that it can have, and the importance of this technology in our day-to-day lives and at advanced levels like medical science, environment, uh, and many more things that can be articulated using nanotechnology. So I'll be giving you the brief introduction, and certainly the aim of the course is basically to understand the importance of these nanomaterials. Not only the importance, but what's the underlying laws of physics that govern these materials to have these extraordinary qualities in terms of technological importance. So, so that the idea is to understand the science of this very small. I'll be just giving a gist of the field, and then after this, I'll try to prepare and draft out some detailed lectures on nanotechnology. Now, uh, the point is, I should start with a very fundamental question that can raise in our minds, and the question is, what is nanotechnology? And to answer this question, it is important for us to have the knowledge of the bulk materials, to have the knowledge of the materials that work at macroscopic level. And if I take an example of, say for example, I take an example of gold. And gold is a very good conductor of electricity. That means if you apply a potential difference across the gold material, the current is going to pass through this material. And when we try to explain the behavior of this material, we have the laws that govern these materials to have those important properties like the conductivity of these materials, electrical conductivity, thermal conductivity, mechanical strength. So these are some of the important properties, and everybody is aware about the properties that the gold possesses, the properties that the silver possesses, the properties that copper possesses. And we deliberate, we explain those materials in the framework of classical laws of physics. And we can explain the behavior of these materials using the laws of classical physics. We have the very fundamental theory for these materials like free electron theory or the band theory. Using these theories, we can explain the behavior of these macroscopic materials. So at room temperature, all of these materials have defined properties. An insulator is an insulator. It's not going to have any other kind of behavior. It is an insulator under normal circumstances, having some range of room temperatures. But the story changes. The story changes when we boil down these materials to small scales. Now, the very first question is that what's going to happen? Uh, is it a universal fact of these materials that gold is always a good conductor of electricity? The answer to this question is no. It's not something like universal law of gravitation, where you can expect that the things happening in the cosmos, they obey the very fundamental laws of gravitation, they obey the very fundamental laws of general theory of relativity. So they happen to have the universality when you apply these equations in the outer space. But here we are talking about the materials, and these materials have certain properties, and these properties cannot be universal. These properties the materials have, they depend on their structure, how atoms are arranged in those materials. Now, for the bulk materials, talking about these conductors or insulators, they can be explained in view of the classical theory of physics. And even if, when we try to explain the band structure of a solid, so suppose we have a well-defined model in condensed matter physics, what's called as Cronin-Penny model. And Cronin-Penny model can be applied to deliberate, to build the bands of these solids. We can theoretically calculate down, boil down the Schrödinger's equation and reach out where we can establish the three important phases of these materials, and we can differentiate a conductor from a semiconductor from an insulator. But the point is, the basic argument that we have, even though we apply these the quantum mechanical equations to these materials, the idea there is that the electron that's within that solid, this electron will never see the boundary of that material. So that's why we say that we explain the properties of these materials based on the classical laws of physics. So what happens here is you apply the quantum mechanical structure to understand the bands that are generated in these solids by simply assuming that the electron will never see the boundary of this material. So the postulate that you have here to explain the properties of these materials seems to have a particle which never will see the boundary of this material. So if you're talking about this kind of material in which electron will never see the boundary, this is what's called as the bulk material. So we understand that how the properties and how what can be a perceived proposition, what can be the perceived action of a bulk matter when you are applying a potential difference across it, and you can explain why some material is a conductor and some other material is an insulator, and so on. So the basic argument that I'm trying to add here is that all the theories that we make use to explain these bulk materials, the basic argument here is that the electron will never see the boundary of this material. So this electron will have a continuum of energies that it will possess, and it will certainly fall in the framework of classical laws of physics. But when we go down to a scale of 1 to 100 nanometers, and we understand a nanometer is a billionth of a meter, and to imagine 1 nanometer, there can be a range of examples. If I take a tennis ball and I take the size of I take the size of this Earth. If I compare the two sizes, on an average, approximately, the size of this small tennis ball is as equivalent as that of 1 nanometer. Okay, if I choose the size of the Earth as 1 meter, then the size of this tennis ball is equivalent to 1 nanometer. So nanometer is a very, very small scale. And when we go to the nanoscale of the materials, the thing that I was telling you, where we could explain the properties of materials using the classical laws of physics, there we find a transition. We find the transition in the properties of these materials when we reach to a scale where we have the atoms ranging from 1 to 100 nanometers. And what can we do at this scale is we can manipulate our atoms and molecules, and once we manipulate them, then we are certainly going to change the properties of these materials. Now, the very first question again in our mind is that what happens? What happens when you boil down your bulk material to a nano scale? What happens, and why there is this kind of thing that the properties of materials that we have, the properties change from being a conductor in its bulk form and then becoming an insulator when it turns down to the nanoscale, or turning into a semiconductor, depending on the arrangement of the atoms. So this nanotechnology, it's not a field of physics alone, it's an interdisciplinary field, and people from different domains of science and social science, they come together and work on this field, because this field has tremendous applications in the coming future, and the applications are already in action in the current times. So that's why this nanotechnology is an interdisciplinary field. It does not belong to physics, chemistry, and material science alone. It has the inculcation, it has the involvement of the range of domains from engineering to medical science. Everybody is involved in it. Now, as a physicist, I would always go back to a beautiful theoretical physicist, Richard Feynman, and I think in American Physical Society in 1959, Richard Feynman said, come on, there is plenty of room at the bottom. This was an argument that was given by Richard Feynman, and the intuition was that certainly you can do tremendous things when you go close to the atomic and molecular scales. And in his lecture, the lecture that he was giving in American Physical Society in 1959, his argument at that time was that why can't we embed all the encyclopedias that we have, all the volumes of encyclopedias, to be stored on the tip of a pen. So this was an argument of this great theoretical physicist, that you can do miles when you go to the bottom. And another important development from the first thing was the theoretical argument of Richard Feynman, and then I think the biggest advancement of the modern times was development of this scanning tunneling microscope, and you could develop the tunneling current, and using the tunneling current, you could map the surfaces of the materials. You cannot only map them, you can also manipulate the atoms and molecules in these nano materials, in the materials which are boiled down to the nano scale. So all the microscopes that have been developed, there are a range of microscopes. We have scanning electron microscope, tunneling microscope, atomic force microscope. They work on the basic principles of quantum mechanics. And these devices, when these devices were developed, the nanotechnology became a possibility. It became a reality in the field of science and technology. So these two arguments, I believe they are the basic bone of what we call nanotechnology. the argument of Richard Feynman and the development of these microscopes. Using these microscopes, you could check the morphology of these materials, and you could even manipulate the atoms of the materials. So, we have had throughout the world an initiative that was started from 2000 to have the national nanotechnology initiative in our country, in India. So we have this this thing going on. We have the people who are working in the field of nanotechnology, because it's going to impact each and every corner of the life. So it does have applications. Nanotechnology has capabilities to design the medicines that can reach out to those portions where the medicines that are made of bulk materials will not reach. And using nanotechnology, we can have precise delivery of the drugs. So suppose there is a problem in my hand, and the problem is somewhere. And using nanotechnology, we can use the imaging as well as the drug delivery system in such a way that the drug will exactly hit the target that it is supposed to hit. So nanotechnology is going to drastically impact our lives in the field of medicine, where you can map, you can image the organs of the humans, and you can target those parts of the organ where you want an impact of the drug. So it may be also an alternative to the rigorous radiation therapies that have been used for a long time to treat cancers, to treat tumors. So nanotechnology is a hope in that domain of science, where a patient has not to go under radiational exposure, which certainly has a lot of side effects, which certainly has a very good probability to kill down the normal cells surrounding the tumor, surrounding these cancerous cells. So nanotechnology can be a new basis that can autoclave the treatment of cancer, and certainly people are working in this domain to achieve these milestones, where they can certainly make the difference. Maybe there is a basis that can be developed using nanotechnology, where you no longer need radiation therapies to treat the cancer patients. And electronics will be certainly revolutionized. It's already in a state of revolution, but it's going to be, your electronics is going to be more faster, and the devices that you'll be dealing with, they are going to become small and small. And energy is the biggest problem of the world, and we are always we're always fond of obtaining, developing, generating energy from sun, and the reservoirs that we have in terms of petroleum or fossil fuels. These things are going to exhaust, and there is the need of having high efficiency solar cells. And I can see the change, a translation, the panels that we used to have five years before and the panels that we have now, and we can find a appreciable difference between the generation of energy using those panels. So nanotechnology is going to play the vital role in getting us out of the dependence on the fossil fuels. And we can see we have been using these panels to charge our batteries. At the same time, the batteries that have been designed their efficiencies are good, and they can store more and more energy. So from storage point of view and from the generation point of view, nanotechnology is playing a vital role. It's playing an extraordinary role to to give us freedom from using the fossil fuels. And environment uh, is certainly an issue in the modern world, and nanotechnology will certainly play a role in purifying water. Water is important for everybody. It's not important for humans alone. It's important for animals. It's important for birds. So these water bodies, how we can restore the purities of these water bodies, nanotechnology is going to play a very important role, and it's playing its role in doing so. And you can generate the sensors. These sensors can sense the purity and impurity of water. So there are, of course, challenges. Nanotechnology, it cannot always have the positive implications on humans. It can certainly have issues associated with it in terms of toxicity, in terms of health effects. And it certainly can be challenging. It can be challenging for environmental impacts. And there is a regular need of issuing ethical and regulatory issues in view of nanotechnology. So, as I was telling you about I believe the most important thing in the field of science, the field of medical science is changing. Now, if I talk about, say, I'll take an example of, suppose there is a general kind of disease. Now, different humans will respond differently to that disease. But as long as the treatments are concerned, we have universal treatments. So suppose there is a disease A, and for this disease A, you have a universal protocol that will be followed for, suppose, for a group of 100 people. But at the same time, there is one important reality, that every person among these 100 people will respond differently to the same disease. So maybe in one case you need a more attention, in another case you need a less attention. In one case the implications may be a little bit different, in another case the implications may be a little bit different. So this difference of responses to the same kind of attack that's going on these 100 people, it has given birth to what's called as personalized medicine. So the quantum of medicine that you are utilizing, it will certainly have an impact. That impact will be different on one person from that of another person. So what is the protocol here is, using nanotechnology, you can build 100 different types of protocols falling in the same framework of the attack on the 100 people. So this is what leads to what's called as personalized medicine. This is how I have understood. It might have a range of things in it. And the next class is the smart materials. And smartness, we understand that how fast a material will react to an action that is happening on the material, and nanorobots and beyond. And as I said, if I go into the framework of the humans, you can design the nanorobots which are filled with the medicine. You can sense them that they have to go to the target, and these nanorobots will go to the target and hit the diseased portion. So these are the important future prospects of nanotechnology that are going to revolutionize, that's going to I should say, dramatize the future world of medicine and the future life. So, to summarize this talk, my intention is basically to let you know what the field is. So the field is something that shows a transition The materials in the bulk scale have different properties, but if you take your materials to the nanoscales, the properties of these materials change. Now, to take an example, gold is a very good conductor of electricity, or its color is yellow. And if you will take gold to the nanoscale of the order of 1 to 100 nanometer size, it may become an insulator, and the loving color that this gold has, the yellow color, it will have a different color. It can have a red color. So the laws of physics are changing. The laws that govern the bulk material, they seem to have no explanation for why the properties of these materials change when you go to the nanoscale. So here, the subject is born. So the subject is born at the edge where the properties of these materials change. Now, edges could be different. Suppose we have a meter scale. We boil down it to the millimeter scale. We boil down it to micrometer scale. In these scales, the properties of these materials does not change. All of these scales are considered to be bulk scales. But the moment you take your material to the nanoscale, when you take it to 10 to the power of -9 meters, when you take it to that scale, the property of this material, which was a universal conductor when you are applying a potential difference across it, it does not behave like that. It behaves in a very different fashion. It tells you, come on, I'm not a conductor, I'm an insulator now. Now, what is it? What is it that makes it different? To answer this, we need a course. We will go through the course of nanotechnology. We'll take the different targets, the different titles, and we will mathematically go around them. We will geometrically try to go around them and to understand why the properties of these materials change. So with this, I would like to end my talk. So in my next presentation, I will go with the very first class on nanotechnology. So a very goodbye to all of you.